Hello everyone, and thank you so much for coming today. I'm Carrie Sewell. I'm the research librarian for the health sciences, and it is with great pleasure today that I introduce Dr. William Irish. Dr. Irish is research professor and vice chair for research in the Department of Surgery at Brody School of Medicine, and co-director of the Big Data and Analytics Research Cluster at East Carolina University. Dr. Irish's major research interests consist of identifications of important prognostic factors of disease and clinical outcomes, and developing statistical models and assessing their clinical utility. Of interest is evaluating factors that affect outcomes in individuals who live in rural areas. Dr. Irish is a member of several professional organizations, including the American Society of Transplantation. He is currently statistical editor for the American Journal of Transplantation and associate editor for clinical transplantation. Please join me in welcoming Dr. Irish.
Well, thank you, and good afternoon, everyone. So this is a talk on determining the appropriateness of statistical methods and research, and this is actually a fairly large topic, right? So I've sort of condensed things down to about 35 slides. And so hopefully I can get through it. This might be part one. We might have to have a part two, right? But anyway, we'll see how it goes. So just by way of outline, so I'm going to talk about sort of what is statistics and why is it important, and talk about different types of data. This really drives the type of statistical method that we employ. What's the difference between an independent versus a dependent variable? And discuss the two main branches of statistics, descriptive and inferential statistics, and kind of introduce or go over some common statistical tests, and then a list of references that provide more detail on different types of statistical tests and assumptions, etc. So what is statistics? So statistics are the primary tools for assessing relationships and evaluating study questions. It allows you to evaluate claims based on quantitative evidence and help you differentiate between reasonable and dubious conclusions. Unfortunately, it's often perceived as a way to get rid of uncertainty. This is not what statistics is about. Data is expected to vary from experiment to experiment. We know this. So statistics is really about quantifying the degree of uncertainty. So learning to interpret that uncertainty in scientific results requires a lot of statistical training, more than what the average sort of scientist gets. So we're not getting rid of uncertainty. We're going to embrace it. We're going to integrate it, and we're going to use it to make decisions. And again, that's driven by the different types of data. So this is sort of a flow diagram of the statistical process. It starts with the study design, constructing the study design, through data collection, conducting analysis, and interpreting the results. So the overall quality of the results depends on the entire chain of events. So a single weak link can produce unreliable results. So when you're reviewing a paper, you're reviewing an article, you're reading an article, there's this whole sort of process that the authors went through to collect the data, to analyze the data, and to interpret those results. And anything that goes wrong in that sort of chain can lead to unreliable results. We can misinterpret results. We can then have false claims. So statistical knowledge helps you use the proper methods to collect the data, employ the correct analyses, and effectively present the results. So this will allow you to produce reliable results, analyze the data appropriately, and draw reasonable conclusions. So I'm going to go over some common sort of methods that we use to describe the data, and based on that, what we can use in terms of how to generalize those results to a population, to infer, to draw conclusions. So what can go wrong? There are many ways in statistics which can be misused and even abused. And really the misuse of statistics, and when you're reading sort of these articles or reviewing these papers, often arises from a lack of knowledge or planning. But it also can be deliberate. We know this. Decisions are made in order to achieve a desired statistical result. Individuals sort of leave out data, they delete data, they run a bunch of tests, they only report things that are statistically significant, quote unquote. And this can lead to a lot of problems, right? So this is a list of sort of the common errors, errors in choice of statistical method, using the wrong statistical method not adhering to certain assumptions, errors in the description and presentation of data, inappropriate treatment of outliers. Often you'll have a result, an observation. That observation may not fit into sort of your perceived notion of what that value should be, and you delete it. That is incorrect. Unless it's an error in reporting, you can evaluate it, but if it's real, you cannot delete it. We have to capture it. It's going to have some sort of effect on our uncertainty depending on the sample size, but it's wrong to delete information. Not verifying statistical assumptions. A lot of the methodology, a lot of the inferences we make, which are probability based, are based on statistical models, and they follow certain assumptions. So it's really important to test for that. And often this is not described in the methodologies, in the statistical sort of analytic methodology of most papers. As an editor for the American Journal of Transplantation, we strive to have all the authors describe the statistical methodology in some sort of detail. If it's complex, then we use sort of a supplemental material. But it's really important that everything be disclosed. And misapplication of non-parametric and parametric tests. And we're going to talk about that later on in the talk. And lack of transparency. So this is non-disclosure of analytic decisions. Again, going back to the kind of the situation where a scientist runs a whole bunch of tests but only reports certain values. Just kind of mitigate that in terms of the statistical process. We really like to define our analytic methodology up front before we collect the data. This is how we're going to look at the information based on the research objectives, based on the type of data we're collecting. And so here's the methodology we're going to use, and we have to stick to that. We just can't run something, it's not significant, run something again, right? This is really inappropriate. So what about the data types? So the type of values influence the ways in which the variables can be summarized and statistically evaluated. So these can be classified into one of four types. It really depends on the type of scale used to characterize their values. So we have nominal scale variable. This is one whose values are categories without really any numerical ranking, such as residence or gender. We have ordinal scale variables. These are values that can be ranked but are not necessarily evenly spaced. For example, stage of disease. So these are categories, but there's a natural ordering to them, right? An interval scale variable is measured as a scale of equally spaced units, but without a true 0 point. The classic example is temperature. Temperature in terms of degrees Celsius and degree Fahrenheit, 0 doesn't mean lack of temperature. So it's an interval value variable. And then there's the ratio scale variable. So this is an interval variable, but has a true 0 value. Duration of disease, time, for example, height, age. These have a true 0. But I kind of think about, even though there's these sort of four scales of measurement, so when I'm thinking about things, I think in terms of whether it's categorical or continuous. So like nominal and ordinal are categorical variables, and then interval and ratio are continuous variables. And as the slide indicates on the far right here, as you increase in the scale, nominal, ordinal, interval, ratio, you're increasing statistical information. So if you're designing a study and you're looking at a nominal level sort of variable outcome, that's going to be less efficient than if you can characterize that measurement on some sort of continuum. Okay? So what do I mean by an independent variable versus the dependent variable? So when designing the studying and planning the analysis, it's really important to distinguish between what an independent variable is and what a dependent variable is. So an independent variable is just that, as the name implies. It's a variable that stands alone, isn't changed by other variables you're trying to measure. Age, treatment, randomized allocation to a therapy, right? This is something that's manipulated by the researcher. This is an independent variable. A dependent variable, as the name implies, is a variable that is dependent on other factors. For example, mortality, hospital cost, readmissions, complications, etc. And what's really of interest in sort of our analysis is kind of what the relationship is between the independent variable, the explanatory variable, and the dependent variable. Does the independent variable cause a change in the dependent variable? So all our sort of inferences and statistical analysis is really driven by that particular type of question. It doesn't have to be healthcare. It can be marketing. It can be any type of study or sort of research condition. So in statistics, there are two main branches. There's descriptive statistics and there's inferential statistics. So descriptive statistics is that branch that is concerned with describing important characteristics of the data set. So this is done by summarizing the data with help of numerical and graphical tools such as charts, tables, and graphs. Inferential statistics is all about generalizing from the sample to the population. So we're drawing conclusions about the population based on results of the sample. So when we have our data, we are going to describe it. We're going to describe important features, characteristics of that data. If it's an epidemiologic study, we're going to look at sort of the summary of the important sort of prognostic variables, etc. Inferential statistics, we're going to take that information and we want to say something about the population. So we're going to talk a little bit about descriptive statistics. So, and you may know this, right? But there are two types of summary measures. There's measures of central tendency, and there's measures of spread or dispersion. So these are what we use to summarize our sample data set. And when you read a paper, they'll have these sort of measures in the paper, and they'll discuss it, right? So measures of central tendency, this includes the mean, and I believe everybody knows what the mean is. The median, this is the 50th percentile, and the mode, the most common value. Measures of spread, this includes the standard deviation, the interquartile range, which is the values between the 25th and 75th percentile. So the interquartile range really is used to describe the spread of the middle 50% of the data. And then the range. This is the values between which all the observed data are contained, the minimum and maximum. So these are the common measures we use to summarize data. Measures of central tendency, measures of spread. And What types of measures we use depends on the type of data. So when you're reviewing a paper or reading an article, it's important that, one, they describe the variables that they're looking at, they operationally define things, so you can get a sense of what type of data they're using. And then that, generates sort of what types of measures they're going to use in terms of central tendency and in terms of spread. So the type of data, the scale of the measurement dictates which measure of central tendency and which measures of spread we should use to describe our data. So for nominal data, we typically use the mode. This is the most prevalent category, right? For ordinal data, this is data categories that have a natural ordering. We use the mode and median. And in terms of capturing the spread or the variability, we use the range and the interquartile range. For interval ratio data, this is continuous variables. We use the median and mean, and we use the standard deviation. So there's nothing really sort of involved in this, right? But again, if you read an article and they're talking about the mean for an ordinal level data, you have to sort of question what that means, right? So I'm going to back up because I just want to mention one thing here. I want to talk about the standard deviation. So this is a good measure of a spread, more so than the range. And it's a good measure when the variable is approximately normally distributed. For irregular distributions, and I'll talk about that in a second, we want to use the interquartile range. Okay? So mean and standard deviation, good measure of spread if our data are approximately normal. For those that are irregular distributions, we want to use the interquartile range. Does that make sense? So what do we mean by distribution? So when I'm talking about this, because this really drives inferential statistics in our statistical tests. So what do we mean by distribution? The distribution of a variable is a listing or function that shows all the possible values of the data and how often they occur. In the world of statistics, there are dozens of different distributions for categorical, for ordinal, sort of nominal, or ordinal and nominal scales of measurement, and for continuous variables. One of the most well-known distribution is called the normal distribution, also known as the bell-shaped curve. And so this is an example of a normal distribution. So you can see that it's symmetrical about the mean, and the peak of this distribution, the mass occurs at the mean, median, and mode. So in the normal distribution, those three measures are exactly the same. Okay? So in some ways, if you have somebody reports a mean and then a median, and they differ quite a bit, then you have to sort of question about the normality of that particular variable. What's nice about the normal distribution is we use the standard deviation rule. So we know that with the normal distribution, that 68% of the observations are going to fall within one standard deviation of the mean. 95% will fall within two standard deviations of the mean. And 99.7, or virtually all the data, all the observations will fall within three standard deviations of the means. So there is a formula that describes the distribution of the normal curve. It's sort of spread and how flat it is, right? This is based on the mean and the standard deviation. So there's an actual mathematical formula. And then we can use that formula to calculate Well, what's the likelihood that if I select an observation at random, it's going to be between 2 points on the curve? Okay? We know that 68% are going to be within plus or minus 1 standard deviation, right? So it's an important distribution to us, to statistics, for a lot of reasons. So here are 2 examples of sort of an irregular or asymmetrical distributions. Both these have a single peak. If the tail on the left of the peak is longer than the right side of the distribution, this is referred to as negatively or left skewed. So retirement age, for example, and test scores usually have an irregular left skewness to the distribution. And you can see that the mean is less than the mean, which is less than the mode. Okay? If the tail on the right side of the peak is longer than the left side of the distribution, this is referred to as positively or right skewed. In this case, the median is greater than the mode and the mean is greater than the median. And examples include like household income, length of hospital stay, length of time in the ICU. These are variables that typically have a right skewed or positive skewness. Why is that important? It's because this will dictate how we summarize it and what types of statistical tests we'll use. So here's a summary of, this table is a summary of the different descriptive and graphical statistics. I'm sure we're all familiar with this. You know, the bar chart. If we have one categorical variable and we use a bar chart, this shows the frequency, so the percentages and the proportions among the different class levels. If we have 2 categorical variables, we use a stack or multiple bars. This is used to compare percentages or proportions within the groups. If we have a continuous variable, we use a histogram. This shows the distribution of results. And again, we use the mean and sort of standard deviation, depending on sort of the distribution. A scatter plot. This is when we have 2 continuous variables and we want to look at the relationship between the 2. And this really helps us to detect outliers. And we use what's called the correlation coefficient, how these things are related, how they're correlated. And the box plot, this is when we have 1 continuous and 1 categorical, and this is used to compare spreads between levels of categorical variables. So I'm going to talk about the histogram and the scatter plot and the box plot in the next couple of slides. But the histogram is important because we want to look at how our variable is distributed. It's going to help drive our statistical methods. This is often never reported in the literature, in an article. But it's really, really important. So the histogram shows 3 general types of information. It provides visual indication of where the approximate center of the data is. We can gain understanding of the degree of spread or variation in the data. And we can observe the shape of the distribution. So when developing a histogram, the variables are divided into several sort of discrete intervals, or what we call bins. 5 to 20 bins are typically used. There are mathematical formulas that you use to calculate the sort of the optimal number of bins. One is the Sturge's rule. And most of your statistical software are going to adhere to a certain default sort of formula. But you can set the bins, right? And the number of individual values that are contained within a bin are then counted and plotted. So that's really the histogram. It's going to show us the distribution. So height of the bars is proportional to the frequency. And here on the left, this is the an example of the distribution of recipient age at time of kidney transplantation. So what does this distribution look like? Well, the tail on the left is longer than the tail on the right. This is left skewed, right? I've actually superimposed what the normal, theoretical normal distribution would look like, that curve there, if we have a mean of 51.6, which is the mean age, and a standard deviation of 13.8 years. So that's sort of theoretically what that normal distribution should look like. Because remember I told you there's an actual formula. I can plug the mean and standard deviation in, and I can draw that curve over the range of my values. So this is just an example of what a histogram could do. So another one is the Box-and-Whiskers Plot. This is used to compare the shape of the distribution of a continuous variable between levels of a categorical variable. And so the plot displays 5 key values. There's the median, which is the solid horizontal line within the box. This is the median. The 25th and 75th percentile. The 25th is the lower edge of the box, and the 75th is the upper part of the box. And then the minimum and maximum. That's the lower and upper whiskers there. So this allows you to kind of very quickly look at sort of the distribution and how it compares among our categorical levels or nominal variables. So in this example, this is an actual paper that was published in Clinical Transplantation from our transplant group looking at the distribution of tacrolimus doses in African American women who express a certain type of gene. And we can see those that have expressed that gene have a higher need for certain doses and a much more sort of variability. So this is a really quick way. Now you'll see that in papers. It's a really nice visual display. Now the scatter plot. So this is used when we want to sort of describe the relationship between two continuous variables. So this scatter plot is very informative because it allows us to look at sort of the overall pattern. So we can determine whether there's a positive relationship, which means that if you increase a variable, you get a corresponding increase in the other variable. So a positive relationship, or a negative relationship, which is the example on the left. So if we increase driver age, we decrease the sign legibility distance. And we can also look at the form. We can see that this looks, fairly linear, right? If there was some curvature, we would see that in the scatter plot, right? So we can look at form, whether it's linear or nonlinear. And this will help drive what we do in terms of our statistical analysis. And we can look at deviations from the pattern, as well as we can look at the strength. How are these observations clustered around that line? What we see, unfortunately, in papers is somebody will have a scatter plot of their two variables and report that there's no relationship, but then they draw a line. Okay? Don't do that, right? No relationship means no relationship. Okay? Typically, if we have a situation where we have a dependent variable, that dependent variable is usually on the y-axis, and our independent variable is on the x-axis. If we're not distinguishing between what's an independent and dependent variable, it doesn't really matter. But typically, we report the dependent variable on the y, independent variable on the x, the explanatory variable. Okay? Everything I've talked about can be done in Excel. There's nothing, you don't need powerful statistical, like SAS. You don't need any sort of powerful statistical analysis software, right? You can do it in SAS, you can do it in SPSS, you can do it in Stata, you can do it in R, but you can do this in Excel. Now we're going to get sort of into the meat of the matter. Now we're going to get into inferential statistics. So, descriptive statistics, so the measures of central tendency, measures of spread, right? What we use and what we report and what we should report is really dependent on the scale of measurement, right? But really in that sort of case, we're describing characteristics of the sample, that our particular data set. Now we want to use that information and sort of infer something, draw conclusions about the population. So with inferential statistics, the concept is to take data, take information from the sample, and make generalizations about the population. So the population in statistics includes all members of a defined group that we are studying. It is defined by a particular set of characteristics such as specific attributes or traits, experiences, knowledge, skills, treatment, etc., right? It's everything. In a randomized controlled trial, we define the target population, we define the study population, we have inclusion, exclusion criteria. These are the set of characteristics that defines the population. Then we go out, we recruit patients, we recruit subjects, we collect our data, we describe it. That's perfect. Now we got to make some decisions, right? What does it all mean? So when we talk about generalization to the population from the sample, we expect the sample, if selected properly, to include the set of characteristics that define the population. Okay? This is probably, in terms of research, is probably the most critical part. One of the most critical parts, right? In epidemiology, if we don't do things correctly, we have selection bias. And this is a problem, right? And bias in statistics means just that. There's nothing I can do to change that. There's no statistical test I can throw at it. There's no methodology I can put in place that's going to change that, right? Bias is fixed. Okay? So selection of the sample, whether it's in a randomized controlled trial, it's in a survey, we have to be very, very careful. Statisticians can sort of minimize selection bias. For example, in a survey, we can do probabilistic sampling. We set the sampling frame. We know what the probability of an individual being selected, what the probability of a set or a sample size of a certain number, what that probability is, right? And we can use that to our advantage, right? In convenience sampling, this can be a problem. It's actually a problem in randomized controlled trials because we set the criteria, then we go out. There's no selection based on some sort of probabilistic sampling, right? We just grab patients. So the question becomes, how representative is the clinical trial to sort of the target population? It's always a debate, right? But with a randomized controlled clinical trial, we're really trying to maximize the internal validity, right? We want to make sure that when we make a comparison, that result is truly reflective of treatment or a program or therapeutic or whatever that is, right? Okay, so inferential statistics. There are two main areas of inferential statistics. There's estimating parameters. This means taking the statistics from your sample data, for example, the sample mean, and using it to say something about a population parameter. So now I've introduced sort of two concepts, a statistic and a parameter, right? And a statistic, for example, the sample mean, is a variable. It is known. It's what we calculate. It's what we observe from the data, right? The population parameter For example, the population mean is a fixed value and is always unknown. We never know what the population parameter is, right? And I'm using the mean, but that could be a ratio, it could be a difference between two means, it could be the difference between two proportions, it could be a relative risk, it could be a hazard ratio, it could be whatever, it could be a p-value, it could be the lower and upper bound of a confidence interval. Those are statistics. They're subject to uncertainty. Now, as a statistician, I'm going to integrate that uncertainty and I'm going to make some decisions about the population. So I'm going to quantify it, I'm going to use it. So the hypothesis test, this is where you use the sample data to answer sort of research questions. You might be interested in knowing if a new cancer drug is effective or if breakfast helps children perform better in school. So it's one thing to describe the sample, it's another to make sort of claims about that data to the population, which is really what we want. So inferential statistic is the mathematics and logic of how this generalization from sample to population is made. And it's really based on probability theory. There's a central limit theorem that's really important, and about confidence intervals and uncertainty, right? So again, this line of reasoning assumes that the sample, that data, is representative of the population. If it's not, for whatever reason, then the inferences won't make sense. They won't align. So what is a confidence interval? So the confidence interval describes the amount of uncertainty associated with a sample estimate, our sample mean, for example, right? Again, we take a sample from the population, we've got data, and we calculate our sample mean and a sample standard deviation, right? But notice, I could take all kinds of different samples from the population. I can have a set of 100 subjects, I could go get a different set of 100 subjects, and I get another set of 100 subjects. It's almost limitless how many samples I can draw, right? But when we do experiments, we only do it once, right? We don't repeat the experiment several times so we can get some idea of what our uncertainty is, right? We do it once. So that statistic has variability, right? There's variability around the sample mean, just like there's variability in our individual observations. There's variability around that sample statistic, right? And we're going to use that to construct sort of a confidence interval, right? And really, the confidence interval has a very simple formula. It's the estimate, in this case it's theta hat, plus or minus some multiplier times the standard error of that estimate. The standard error of the mean, for example, right? Or the standard error of our differences in means, or the standard error of a relative risk. And the multiplier depends on the standard normal distribution. The typical value is 1.96 for a 95% confidence interval. So when you're reading articles, when they present intervals, it's usually the 95%, right? So the wider the interval, the less confident we can be about the estimate of the population parameter. So how do you interpret a confidence interval? So when you're reading a paper, a lot of people misinterpret what the confidence interval is, right? Okay? So from a non-technical perspective, it's the range of plausible values of the true parameter. But in technical speak, it means, again, if I could repeat my experiment 100 times, and I calculate the mean for each one of those experiments, and I calculate what the confidence interval is, 95% of those confidence intervals are going to contain the true parameter. 5% are not. Okay, so it provides our level of confidence. So it's a way to sort of take that uncertainty and sort of quantify it in terms of sort of a lower and upper bound. And then we can use that to say, well, how certain are we, right? That's a really wide confidence interval. I'm not convinced that what they've got is really biologically sort of feasible or plausible. So now we get into hypothesis testing. So this kind of refers to the formal procedures used to accept or reject statistical hypotheses, right? And so there are certain tests, right? Or certain steps. You decide on your hypothesis and you derive the null. You consider the measurement level, scale of the variables. You analyze and you select appropriate statistical tests. And I'm going to give you some recommendations on which types of tests to use under different sort of conditions, right? You conduct the test, you derive, and you evaluate the p-value. And evaluate the p-value is somewhat of a controversial thing, right? And I'm going to talk about that. And there was a recent commentary in Nature, Dr. Lee had sent me, about the p-value. And getting away from the term statistically significant, right? So if I read any of your papers, I don't want to see statistically significant or statistically non-significant. Statisticians want to get away from that phrase, okay? So what's the null? The null specifies a single value and always has an equal sign in it. For example, the mean equals 0. The mean difference equals 0. The relative risk equals 1, right? There's always an equal sign. And this is about the parameter, right? Not about the statistic. The 0 is the parameter, the population parameter. So it says nothing happened, there's no difference, right? No evidence of a difference. The alternative, the research hypothesis, specifies a range of values and always has an inequality in it, right? The mean difference is not equal to 0. The relative risk is not equal to 1. So something happened, there's a difference, etc., right? And how we judge that is based on sort of the p-value, right? And the p-value is generated from the statistical test that we use. So the test statistic. So again, got our data, we've described it, we have our hypothesis, we want to test our null versus our alternative, right? We know the scale of measurement, we know how it's distributed, and now we have to choose a test. And again, I go back to sort of this dichotomy of categorical versus continuous, right? If it's categorical and nominal, we're going to use what's called the chi-squared test, okay? If it's ordinal, we're going to use a non-parametric test. If it's continuous variable, and that data is skewed, we have some sort of irregularity in it's a irregular distribution, we're going to use a non-parametric test. If it's normally distributed, we're going to use a parametric test. Okay? So here are common single comparison tests. Typically, we want to compare the averages of two independent groups. Patients got treated or didn't get treated, for example. Our dependent variable is continuous. Our independent variable is nominal. In fact, it's binary. There's only two groups, two mutually exclusive groups. So the parametric test, if our outcome is normally distributed, is the t-test, right? Independent t-test. Everybody familiar with that? Okay. If it's non-parametric, if it's ordinal, for example, or the data is skewed, we use what's called the Mann-Whitney test or the Wilcoxon rank sum test. These are equivalent tests. Okay? What's non-parametric about that? What it means is that the test statistics, we're not assuming it follows some sort of distribution, right? All we're doing is saying we're going to rank our data, right? We're not doing the analysis on the individual observations, but we're ranking them. And we're going to see how those ranks are distributed. And that's what a non-parametric test does. If you want to compare the average of three or more independent groups, and your dependent variable is continuous, and obviously your independent variable is nominal, then you use a one-way ANOVA. Okay? For a non-parametric test, the Kruskal-Wallis test is used, right? So it's a non-parametric equivalent to the one-way ANOVA, right? Again, all it's doing is ranking things, using the ranks. If we're looking at the average difference between a paired sort of matched sample, like weight loss before and after diet, so we have same measurement on individual more than once, then we're going to use a paired t-test. So we got a continuous variable, independent variable is usually a time or some sort of condition, and we use a paired t-test. Okay? And then the non-parametric equivalent is the Wilcoxon signed rank test. So 3+ measurements on the same subject. So we're kind of generalizing the sort of the matched sample. Use what's called a repeated measures ANOVA, and the non-parametric equivalent is the Friedman test. So these are very common tests that we use. In terms of tests of association, if we want to look at the relationship between two continuous variables, then we use Pearson's correlation coefficient, and the non-parametric equivalent is the Spearman's correlation coefficient. So these can be done, again, all this stuff can be done in Excel. You don't need special software, right? Predicting the value of one variable from the value of predicted variables, or looking for significant relationships. If we have a continuous variable and we have a lot of independent variables, we're going to use what's called a linear regression analysis, right? Typically called ordinary least squares regression. If we have our data is skewed, then we want to use some sort of transformation. We want to get it to a state where it is approximately normally distributed, right? Because that's a powerful sort of test. If we're looking at the relationship between a number of independent variables against a dependent variables that's binary, like disease, yes, no, vaccinated, unvaccinated, then we're going to use logistic regression. Okay? There are generalizations of this in terms of survival analysis and time to event analysis, right? But that's a whole separate lecture, because that's not a trivial analysis, right? Okay? Looking at the relationship between two categorical variables, we want to see whether the two categorical variables are independent. We use the chi-square test. So all these things are sort of things that we typically do. They're driven by the type of data, driven by sort of the distribution, whether we use a parametric versus a non-parametric test. And when you're reading articles, they should be describing these things. You shouldn't have to try to figure it out. They should be describing what they're doing, right? And if there's uncertainty, then there's a problem. So if you have one continuous variable and several independent variables, there are different sort of techniques. We use multivariable linear regression, like I kind of described. We can use the two-way ANOVA. If we have sort of repeated measurements, we can use the two-way repeated measures ANOVA. Then we get sort of the mixed ANOVA is a little bit more complicated. Then we have analysis of covariance, right? Where we have a baseline, then we have a follow-up value, and we want to compare the follow-up value between the two treatments, but we need to adjust for the baseline. That's an analysis of covariance, right? Okay? But all these are driven by sort of the type of variable that we have and sort of the conditions, right? But we're going to get a p-value. We're going to get a p-value of all this stuff, right? And then we have to kind of decide what to do based on that sort of p-value. And these statistical tests are really driven by, again, not only the type of data or the scale of measurement, but they're also driven by that null hypothesis, what you're trying to achieve, right? So these parametric tests assumes that the data follows a particular distribution, and the t-test, the ANOVA, your regression, linear regression analyses, they all assume the data is normally distributed. Okay? This is the assumption. This is the one thing that's never really described in a research paper, right? How I have data, I'm using a multivariable linear regression, but I present the results, but I never describe how did I assess the assumptions of that model, right? And normality is one of the big assumptions, right? And you can say, well, what about non-parametric? We just use a non-parametric test. That's fine, but parametric tests are actually more powerful than non-parametric tests. So we just don't want to go to the default and we'll just do all non-parametric tests, right? Because you're going to lose statistical efficiency in that case, right? So we want to utilize the power of that normal distribution in our parametric sort of analysis. So here a slide sort of describes different statistical tests for normality. So you can use these, right? Statistical tests include the Shapiro-Wilk and the Smirnov, I can't remember the guy's name, but the Smirnov test, right? But the problem with these is that they're unlikely to detect non-normality with small sample size. So if you have a study in which the n is less than 20, using these things can be problematic, right? And at the same time, they're too sensitive if you have a large sample size. For example, your sample size is greater than 50. And they're also sensitive to outliers. So the recommendation is to evaluate the normality using the histogram or what's called the quantile plots for small samples. And so for different parametric tests, for an independent t-test, we check for normality of the dependent variable by the group. For a paired t-test, we check the normality for the paired differences, because that's what we're analyzing, the difference. For one-way ANOVA, we check for normality using the residuals. Residuals are sort of what I observe for that individual and what my expectation is based on the one-way ANOVA, based on that statistical model. The one-way ANOVA is a model. The two-way ANOVA is still a statistical model, right? Linear regression is a statistical model. In fact, the one-way ANOVA and two-way ANOVA are really just linear regression, what we call a general linear model. They're just subsets of it, right? So they're not necessarily totally different things. We just call them by different names, right? And for a repeated measures ANOVA, you check the residual at each time point. And for the simple linear regression, you use residuals. Again, all this stuff can be done in software. All this stuff should be disclosed in a paper. How things were checked. If I fit a model, I know the statistical model has certain assumptions. Normality is one of them. How did the authors check it? So the probability. So now we've done our test. We've got our test statistic. We've calculated the p-value. So what does the p-value really mean, right? The p-value is the probability of observing differences as large as or larger than the difference actually observed, given that the null hypothesis is true. That's really important. So if we're comparing our treatments, the null is that there's no difference, right? So what's the probability of observing that difference, the difference in our sample means, for example, given that the true difference is 0? That's what a p-value is, right? You decide on the odds for casting your decision in favor of the null and alternative hypothesis. There is historically this sort of threshold value of alpha equals to 0.05. The p-value is less than 0.05. It's statistically significant. If it's greater than 0.05, it's statistically non-significant. So we want to get away from that. Statisticians want to get away from that sort of dichotomy of yes, no, because there's really no difference between a p-value of 0.049 and a p-value of 0.051. Okay? So the p-value shouldn't be the sole determining factor in terms of what we decide. The p-value plus our statistics plus our confidence interval, the totality of evidence is what we use to make decisions. And again, in hypothesis testing and statistics, nothing is proved, right? So you have to be careful, right? This is a figure that was in this paper that was recently published in Nature, right? You can see that the sort of that upper one that says significant study, that's a low p-value, and then the red line is a non-significant study because of a high p-value. But the observed effect, the point estimate, is the same in both studies. So these two studies don't contradict each other. They're not at odds. They have the same point estimate, just that one is less variable than the other, right? But if you just go ahead and say, well, non-significant, well, I published this as significant, then, but I got, I did a study in which it's not significant. I sent it to a journal, and they don't publish it. So that's a problem, right? So be careful. A high or low, a high p-value doesn't necessarily mean that you don't have a positive sort of result, right? So here are some references. And again, I took statistics and condensed it down to 35 slides, right? But the kind of take-home message is that there's uncertainty. We want to capture that uncertainty. We can quantify it. We have statistical methods to do that. And based on that, we can make decisions. But we have to be careful about those decisions in light of sort of the totality of evidence that we have, right? And here are some references. This last one is actually a website. It's a useful resource for quick definitions, kind of what things mean. There's this one that was published in 1995, so Problem Solving, a Statistician's Guide. This is actually a really nice book because it'll go into details about all the different sort of statistical tests, right? But they have a common theme. And what I've presented can be utilized in Excel. You don't need sort of special software, but there are situations, there are sort of study design conditions and number of variables, et cetera, that can make the analysis complicated. And that's why I have a job, because that's what I do, right? But these are sort of things that are typically reported in the literature, things that are done. They've been well studied, well validated in terms of statistical theory, et cetera, right? So thank you. So time for questions or, yeah?
So what do you do with those results? I mean, it tells you, it basically just predicting the result. So it either comes out as it did or it didn't, but you know nothing about how you created the result. As far as you had no process behavior chart.
You mean in terms of like the p-value or?
Well, no, just what do you do with it? I mean,
You
it says it worked or didn't work, correct?
Well, that's sort of, we're trying to get away from that kind of mindset, right? And
So again,
but even though there's sort of this push to kind of get away from this dichotomy of yes, no, fail, didn't, right? I think that's what you're trying to get at, right?
well,
The
I'm
result.
also trying to get it, but either way, so what? What do we do with it?
What do you do with the results?
Yeah.
Well, you have to kind of, you report those, and you report those in the context of what, sort of what you're trying to achieve. And
But you,
in terms of the discussion, then the results are sort of put into sort of context of the real world in terms of the population.
because I would think you'd want to think, how do we improve the process? Because that's what determined the result. But you have no process measures.
Well, the statistics, sort of there is a process, right, in terms of how we go about designing a study, how we choose our measurements,
Correct.
right?
Uh-huh.
Sort of, and that's really based on biology or sort of what the sort of theoretical conditions. We, based on that, we formulate. We have our research objectives. We formulate our hypotheses, right? If that's what we're doing. Some things are exploratory, right? But if we're trying to sort of if we're kind of setting things up to sort of test those hypotheses, we know the types of variables we're doing. We then sort of develop the strategy up front, right? So for example, I've been involved in clinical trials where we'll write a very extensive analysis plan before we collect the data. And this is our sort of roadmap to what we do. We don't deviate from it. We can deviate, but that can cause problems, right? Especially in sort of the drug development regulatory world, right? And so, there's a certain power to that, right? But you have to write that in an intelligent way, and that's really based on sort of what you're doing, the types of measurements, what you're trying to achieve, right? Then once you get the data, then you execute on the plan, right? Then you make your decisions. But we want to get away from this sort of significant, statistically significant yes, no kind of thing, this sort of 0.05 sort of threshold, right? Which is very pervasive in the last 65 years, right? 70 years in statistics.
I guess my question is, but you're still basing everything on your result.
Of course.
Not based on what you do. So, in other words, use an outcome to determine whether you change things, which is exceptionally problematic.
In the absence of mediators, you're talking about mediators, right?
What do you mean by that?
Like in psychological statistics, I mean the mediators between the original, all the pieces in between. I don't know that matters quite as much in some of the.
Oh, okay. Well,
Well, you're sort of getting at,
I'm looking at it from a process behavior kind of
but
perspective.
you have to have data, right? You got to make some decisions, right? You got to do something with it. It's one thing to describe it, but who cares, right?
You're describing the results now.
Yeah, you're just describing the results. But we want to take that description now. We want to kind of now say something about the population in which that sample is drawn, right? Now, all this sort of, I didn't get into this, right? But there are sort of two philosophies in statistics. There's what's called the frequentist approach. There's a Bayesian approach, right? You're sort of converging on the Bayesian, which means that I have a sort of preconceived notion of how things behave, right? Now I'm going to collect some data. Does that data change that sort of a priori kind of notion? That's the Bayesian sort of philosophy.
Okay, well, thank you.
Yeah.
Appreciate it.